So this video is going to dig deep into process control charts. But before we do that, let me mention if you're interested in a free Lean Six Sigma White Belt certification course, you can access one at sixsigmasociety.org. Okay, so let me first introduce control charts. A process control chart helps us determine if a process is stable over time or if a change was effective. Now, the way to look at these control charts is that on the y-axis on the left-hand side is a CTQ measurement, something we're measuring to see if we're meeting customer expectations. And then on the x-axis on the bottom, you have time. We monitor that CTQ measurement over time to see if it's stable or to see if an improvement was effective. We may watch and monitor that CTQ before the improvement as well as after. So a few example CTQs that we could monitor include things like if you make paper airplanes, maybe you monitor flight distance in feet over time. Or if you produce phone batteries, maybe you monitor battery life in hours. If you create websites, you could look at things like page load time in seconds. You can monitor that. Or if you ship packages, you could monitor delivery time in days or hours. So these are CTQ measurements that we could monitor on our control chart. And then here's an example of a control chart and some of the elements inside of it. So on the top and the bottom, the red lines in this example are what we call the control limits. Those are always plus or minus 3 sigma, or 3 standard deviations from the mean. And then if we go above or below those control limits, we call that an out of control point or special cause variation. And we'll talk about what that means in a second. And then the line in the middle is the process mean or the average. And then you see your data points kind of going up and down over time. Now we should talk at this point about two different types of limits. On our control chart, we set these things called control limits. They're statistical, and they are plus or minus 3 standard deviations from the mean. We could also call this the voice of the process. Specification limits are different. They're based on customer requirements, the VOC. And so it's important to note here that even though the control limits are shown, it might not be the specification limits. Specification limits could be narrower, or they could be wider than those control limits. Now you can think of control limits as being similar to warning tracks in a baseball field. Now this dirt track in the back of the baseball field is used by the outfielders, so if they're looking to catch a fly ball, they don't get distracted and run into the wall. They'll see the dirt path and know that they ought to stop or slow down, redirect their course to make sure they don't hurt themselves. Now when we look at a control chart, we may talk about two causes of variation. The first is special cause variation, and that's sporadic and unpredictable. It's easier to correct. And then common cause variation is more common and predictable variation. This is more difficult to correct. It's more systemic. Now, here's an example of these two types of variation. Think about a process of driving to the office. Special cause variation could be a car accident. So if you're monitoring the time it takes to travel to the office, if there's a car accident, it's sporadic, it's unpredictable. It could make the time it takes to get to the office much longer. Now that's easier to correct. If you know that there's an intersection or an area of the road that's highly prone to accidents, you could do something to prevent that. Add a stoplight or have a police officer monitor it periodically. There's things you could do to correct that. Now, common cause variation, if you think about our process of driving to the office, and if we monitor that process by tracking the number of minutes it takes to get there, it could be, in this case, typical traffic. That's common cause variation. It's more common, more frequent, and it's more difficult to correct. It's easier to kind of prevent an accident than to try to free up all the roads of traffic. Common cause variation is much more difficult to correct. Now, what's important here is that as you monitor these control charts, you're going to be looking for special cause variation and trying to understand why that's occurring. But you should note here that SPC indicates when a process is out of control, but not why it's out of control. So it's going to need some investigation. So now we're going to talk about different types of control charts. So you've basically got 6 or 7 common types, and they're separated by whether they use continuous data or attribute data, like tracking the number of defects or defectives. So with continuous data, The first chart is the IMR chart, or the individual's moving range. So this works really well when production is low volume because it shows individual values on your chart. And this is probably the most common type. It works well when your production is low and you've got continuous data. Now, when production is a little bit higher volume, you could use the X bar R or the X bar S chart. And it's going to show, instead of individual values on your chart, a subgroup of values and then the average of those values. Okay, so those are the most common types for continuous data. Now, when it comes to the X bar R, the R stands for the range and the S is for standard deviation. And we'll talk about that a little more later. This is just giving you kind of an overview of these charts. With attribute data, you've got basically 4 of the most common types, the C, U, NP, and P. Now with the C, you're tracking the number of defects per subgroup where the sample size is constant, the number of defects per subgroup. With the U, you track the defects per unit, and you're tracking defects per unit because the sample size is variable. It could be changing. And then with NP and P, instead of tracking the number of defects, you're tracking defective units. Okay, so if there could be multiple defects in one unit, but we would just call that one defective unit. So with the NP chart, you track the number of defective units per subgroup, where your sample size is constant and oftentimes greater than 50. With the P chart, you're tracking the percent of defective units when the sample size is variable. So with the NP, your sample size is constant, so you can just use the number of defectives. With the P, because the sample size is variable, you've got to use the percent of defective units. So with the CU and the NP and P, you've got to think about, am I tracking defects or defectives? And is my sample size constant or is it variable? That helps with your control chart selection. Now, if it's helpful, we put together this little device to help you remember the last 4 charts related to attribute data. So you could say CU later defects. So C and U deal with defects. And NPP deal with defectives. So you could say detective NPP handles the defectives. So CU later defects deal with defects. And then detective NPP handles the defectives. Those 2 chart deals with defective units. So here's an example of the first chart, the IMR chart, or the individual values moving range. So the individual values are just that, so every point on that top chart is a separate value. And the moving range is the range between 2 subsequent measurements. Now in this example, we're monitoring pH levels, so that's our CTQ measurement, and we're monitoring a process for producing liquid detergent. And we measured the pH of 25 consecutive packages of detergent. And so each of those points on the top represents a different detergent or different package. And you'll notice that about at measurement 8 there, you have an out of control point above the control limit. So you've got your individuals up on the top, and then down below is the moving range, the range between 2 subsequent measurements. And it gives us some idea of the variation in the measurements here. And then we've got the X bar R chart. So on the top, instead of showing us individual values, it's showing us the average of a subgroup, because in this case, production is higher and we can't put every point on the chart. And on the bottom, it's showing us the range of the subgroup. So here's the example. We're monitoring a process for producing camshafts if we make parts for cars. And we measured the length of 5 camshafts during each of 3 daily shifts. So each of those points up on the top represents the average for 5 camshafts. And then at the bottom, it's the range of that subgroup. Every data point represents the range of 5 camshafts. So now let's look at the X bar S chart. This is a little different from the previous one, just with one change. So we're still looking at the average of a subgroup, the X bar, but then we also look at the standard deviation of the subgroup as opposed to the range. Okay, so here's the example of a process. We're monitoring a process for producing canned food, and each hour we measured the weight across a subgroup of 10 cans. So we're measuring the weight of the cans, that's our CTQ measurement. And so up on the top, each point represents the average of 10 cans. And then down below, within that subgroup of 10 cans, every point represents the standard deviation of a group of 10. Okay, so this is the X bar S chart. Then we've got our C chart. We're moving from continuous data to attribute data. And it's attribute because we're checking if it's a defect or not, or if it's defective or not. Now with the C chart, we're looking at the number of defects per subgroup where the sample size is constant. Okay, so in this case, we're monitoring a process for printing wallpaper, and each hour we sampled 100 feet of paper and counted the number of defects. So each hour we sampled the same length of paper, that sample size was constant, 100 feet of paper, and we counted the number of defects we saw, like misprints as an example. Then we can look at the U chart. This is a little different from C. The only change is that the sample size is variable. So we're still looking at defects, but it's the number of defects per unit, not the total number of defects, number of defects per unit. So in this example with the U chart, we're monitoring a process for producing insulated electrical wire, and we counted weak spots in randomly selected wires that are various lengths. So we had these randomly selected wires that were a variety of lengths. We've got this variable sample size, and so we're looking at the number of defects per unit, not just the number of defects. We've got this variable sample size. And then we'll move over to the NP and the P chart. We'll go from tracking defects to defectives. So we're looking at the number of defective units per subgroup when the sample size is constant and greater than 50. So we're monitoring a process for producing light bulbs, and each hour we counted defectives among 500 light bulbs. So how many of those 500 light bulbs were defective? And that sample size is going to stay constant. So each hour we're measuring 500, not 505, not 510. It's going to stay 500 as our constant sample size. And then here's our P chart. Okay, so this is similar to the NP. We're tracking defective units, but because the sample size is variable, we're going to look at the percent of defective units per subgroup, not just the number. So here's the example in this case. We're monitoring a process for answering customer support calls. And each day we record the number of total calls and the number of unanswered calls. So the number of total calls changes. We've got this variable sample size, so we're going to use a P chart in this case. So now that we've talked about different types of control charts, we need to talk about tests that are used as these control charts are reviewed. But before that, we need to talk about Walter Shewhart, who's really deemed the father of SPC. He created these rules and tests to detect process control issues. And now the rules have evolved over time, and as you go to different organizations, you might see them look slightly different, but they're all just about the same. Okay? So the other thing I want to mention here is that in the download section of this page, you're going to see the SPC test handout. So not like you have to memorize all of these right now. You can go back and review them later. And all of these 8 tests we're going to talk about are used for detecting special cause variation. So we talked about special cause and common cause variation. These are used for detecting special cause variation. And the other thing we should mention here is that we need to remember that SPC indicates when a process is out of control, but not why. It might need some further investigation. It's not really going to mean that there's a big problem right away. It's just that it needs some further research. We might need to understand what's occurring. Okay, so now let's talk about these 8 tests. The first test is the most common. It's rule number 1. When there's 1 point more than 3 standard deviations, or 3 sigma, from the mean, either above or below it. And then rule number 2 is when you have 9 or more points in a row on the same side of the center line, or the same side of the mean. It's not a common thing, and you want to understand why that's occurring. Rule number 3 is when you have 6 or more points in a row continually increasing or decreasing. You're seeing a trend here, and you want to understand why that's occurring. Rule number 4 is when you have 14 or more points in a row alternating in direction, increasing then decreasing, up and then down. Not very common. You want to understand why that's occurring. Then there's rule number 5. When you have 2 out of 3 points, at least 2 out of 3 points in a row, more than 2 sigma from the mean in the same direction. Okay, that's what these 2 red circles represent. Now, Rule number 5 and rule number 6 are similar. Rule number 6 is when you have 4, at least 4, out of 5 points in a row, more than 1 sigma from the mean in the same direction. Again, these are uncommon things. It's just that rule number 5, we talk about more than 2 sigma away, and rule number 6 is just more than 1 sigma away. And then rule number 7 is when you have 15 points in a row, all within 1 sigma of the mean on either side of it. Okay, so this could actually be a good thing. It might be a reduction in variation. We just want to understand why that's occurring. And rule number 8 is when you have 8 points in a row with none that are within 1 sigma of the mean. And the points are in both directions from the mean. Okay, so it's actually somewhat similar to 5 and 6. Rule number 8 says 8 points in a row with none within 1 sigma of the mean. And so it looks like you might have an increase in variation. We want to understand why that is occurring. Now, if you use Minitab to prepare your control charts, you have options to select your desired test. So you could use one or all 8 of them. And then you have a chance in some cases to change the sigma that you want used in the test. So you have some customization there. Now, these 8 are the most common, but it doesn't mean it's the only ones that you're going to see. All right, now let's try this out and let's prepare a control chart for continuous data. So let's imagine we have an e-commerce website. We want it to be fast and responsive, and so we evaluate loading times against targets. We want our website to load fast. And to help us kind of frame this problem and understand why it's important in this scenario, I wanted to share some highlights from an article called How Loading Time Affects Your Bottom Line. It's really interesting. So it said that 73% of mobile users say they've encountered a website that was too slow to load. And I actually think that number is probably higher. I think most of us have found mobile sites to be slow to load. And 47% of consumers expect a web page to load in 2 seconds or less. And 40% of people abandon a website that takes more than 3 seconds to load. We've had that experience. We've gotten tired of waiting for a website to load, and so we just abandon it and go to somewhere else. Now, if a site makes $100,000 per day, a 1-second delay could cost $2.5 million in sales each year. And so those loading times are important for e-commerce websites. It becomes an important measurement that they want to track and monitor over time. It's where a control chart can come in handy. So let's imagine this scenario. We've collected some data and we sample load times over 15 days. And each day we take 10 measurements. So we have 150 measurements. So it might not make sense in this case to use an individuals chart because we probably have too many points. So maybe what we want to do is use maybe an XR or an XS chart because we have production that's higher volume or measurements that are higher volume. And let's show a subgroup of values, basically the average of measurements for each day. So in Minitab, if that's what we're going to use to prepare our control chart, we could say that all our observations are in one column and the loading time is what we're looking at. And our subgroup sizes are based on the day. Okay, so we have 15 days, and for each day we're going to average the load times. And what we want to do is we can check to make sure that all of the tests are being used. For this example, we'll just apply all of the 8 tests that we talked about. And so when we generate our control chart, it looks something like this. And there's a few problems that we can run into or notice here. The first is that we've got at point number 3 or sample number 3, we have a point that's below the line. Okay, that's an out of control point. And in this case, because we want our loading times to be faster, that may not necessarily be a problem. It's a smaller value. And then we've got tests 5 and 6, so rules 5 and 6 that have been violated. And it'll show us in Minitab, it'll explain those results to us, because if we just look at the red number 5, that might not make much sense. So in your output, you're going to see something like this. It'll say test number 1 failed, and it's 1 point more than 3 sigma from the center line. And then it shows you rule 5 and 6. So rule 5 or test 5 was 2 out of 3 points, more than 2 sigma from the center line. And 6 was similar, it was 4 out of 5, more than 1 sigma from the center line. And it shows you at what points they failed. Now I think what a bigger problem is here though, is that if we have and we want our website to load faster than 3 seconds, really less than 2 seconds, we've got a serious problem here because our control limits, even our lower control limit, is above that point. Our lower control limit is 3 seconds, or just a little above 3 seconds, and we want it to be a lot less than that to make sure customers don't abandon our website and go somewhere else. And so it's true we've got some problems here, some tests that have failed. We might have a bigger issue. We're well above the loading times that we'd be expecting. And so a control chart can help us understand that and investigate issues that are coming up. So now let's look at a control chart with attribute data. Okay, so let's imagine this scenario. We want to track medication errors at a hospital. So you manage a hospital and you evaluate the medication error rate. For example, the wrong time, the dosage, the medication, and you want to understand errors per patient. In other words, defects per unit. How many medication errors do we average per patient? And so to kind of help us frame this problem a little bit better and to think through it and understand it here, this is something from the American Nurse Today magazine. So it says, mistakes involving medications are among the most common healthcare errors. Medication errors lengthen hospital stays, increase inpatient expenses, and lead to more than 7,000 deaths annually in the United States. Each error costs an estimated $2,000 to $8,750. So medication errors are a big problem. We want to understand that, map it on a control chart, and see what issues might be occurring and investigate those further. So here's our data that we're going to take a look at. So let's say we monitored errors each week for 25 weeks. And we're interested in defects per unit or errors per patient. And our sample size is variable. We've got the number of patients here. So you look at these samples over 25 weeks, and it shows us the errors or the defects on the left side and the number of patients or the sample size on the right. And we're looking at errors per patient. And as we think about what attribute control chart to use, we want to remember that the sample size is variable. That's going to be key here. But also we want defects per unit. Okay, so if we look at our control chart selection sheet, we probably want to go with a U chart here because we want to track the number of defects per unit or errors per patient, and we have sample sizes that are variable. So our U chart is going to be our best option. And as a reminder to kind of remember the difference between C and U and NP and P, here's something to help you remember that. So we say CU later defects. So C and U look at defects. And then there's detective NPP, which handles the defectives, the number of defective units. So we have defects and then defectives. And we can also think about, when we're looking at distinguishing between the C and the U, the number sign comes before letters when alphabetizing. So if you look at the C and the C is the number of defects, and the U is the number of defects per unit. Okay? And so anyway, that may be one way to help you think through and remember the distinction between C and U and NP and P. We've got the defects and the defectives. Okay, so if we're going to use, if we're going to create a U chart in Minitab, we're going to list our variables here, and that's errors, the number of defects we're talking about. And our subgroup sizes are the patients, and those are variable. And what we can do is select our tests also. Let's go ahead and select all 4 here, the 4 that are made available to us with the U chart. And then we'll generate our chart, and we'll see that we have 2 points that are above our upper control limit. And so we want to go investigate those and understand why that might be occurring. We really want to try to cut down medication errors at hospitals because it's detrimental to our patients, but can also be very expensive. And so we want to understand and address those 2 issues that we're seeing and improve our error rate over time. So thanks for watching. If you're interested in learning more, don't forget to check out the free Lean Six Sigma certification course at sixsigmasociety.org.